Okay, so in this video, I'm going to be going over what a limit is and how we can use limits to analyze functions and this importance in calculus. So to understand what a limit is, first we have to go over what the definition of a limit is. So this is the informal definition of a limit, and we say if f of x can be made as close as we like to some number a by making x sufficiently close but not equal to x equals b, then we say that f of x has a limit of a as x approaches b. So I'm going to explain what this means graphically. So let me draw a little scale here. And let's say we had some function f of x here. We don't have to say exactly what it is, it's just some function f of x. And we have some x coordinate here, which is b. This is the x coordinate b. And therefore on the graph what we have is the point b, f of b. Right? Now we want to, and a lot of times in calculus, we want to think about what's happening to the function, in this case f of x, as x approaches a certain value. In this case, we're going to think about this value b. And what we use is this notation called limit notation. And what we do here is we say lim, this means the limit. We put the variable we're analyzing here, which is x. We do an arrow, which means as x approaches, and we put some value in for x, which in this case is b. So the limit, what we say here is the limit as x approaches b of f of x is going to be a. We want to know what value does this limit converge to, does f of x converge to as x approaches b. So in this case on the graph, this limit b, or a rather, this limit a is going to be right here. So this is graphically what's going on. As x gets closer and closer to b, right here, what does f of x get closer and closer to? And the thing it gets closer and closer to will be the limit a. So this is a very important concept in calculus. It is very important for defining what differentiation is, which we'll learn about, and also for integration, which we'll also learn about eventually. So let's go over a few examples of how we can find the limits of different points on a graph. So let's say you're given the following question here. Find the limit as x approaches 2 of x. What value does x approach as we make values of x, what value does f of x approach if x equals f of x as we make x closer to 2? So I'll draw a graph for this first one just to help reinforce the concept visually of what a limit is. Alright, we got some scales here, or some arrows rather. We got a line, y equals x. And let's say we put in some values, 1, 2, 3, 1, 2, 3. We want to know as x gets closer and closer to 2, what is this function here going to get closer and closer to? This function being x. Well, we can see that as it gets closer to 2, the function will get closer and closer to 2 itself. So this limit is just 2. And what you notice is that for most limits, you can just substitute directly the value that the value x is approaching directly into your function, and it'll give you the answer. Not all the time. A lot of the cases it won't, and you'll have to use other strategies, including some limit laws. But in this particular case, this is quite an easy one to do. It's pretty obvious. You can just substitute in and you'll find the answer. But that's not technically what you're doing. You're interested in what the value as x gets closer and closer to a certain value is, not actually whether or not that function is defined at that point, which is what you're doing if you substitute. But regardless, that will still give you the right answer a lot of the time. So let's do another one. Find the limit as x approaches 3 of x squared. And again, if we make x closer and closer to 3, we'll see x squared will get closer and closer to 9. So we'll see that this limit is 9. So this is a pretty easy one again. If you directly substitute 3 in, you can get the answer quite obviously. So usually this will work. But now I'm going to show you an example where using this strategy won't actually work. So let's say I give you the following question. Find the limit as x approaches 1 of x squared minus 1 over x minus 1. Now you can't substitute x equals 1 to this, because if you did that, you get 1 squared minus 1 over 1 minus 1, which will be 0 over 0, and that's an indeterminate form, which we don't have the tools to evaluate. So that won't work in this case. You can't just substitute that value directly in. But instead what we can do is we can recognize the following. We can see that x squared minus 1 over x minus 1 is in fact just equal to x minus 1 times x plus 1 over top of x minus 1, because this is the difference of squares in the numerator. And if we cross out these common terms here, we'll see we're left with just x plus 1. So what we're actually finding is the limit as x approaches 1 of x plus 1, which if we were to substitute it in, we just easily see that it's going to converge to 2. So this is the value of this function here. Even though the function is not defined at x equals 1, the limit still exists, because the function is still going to converge to this value here, whether it's defined at x equals 1 or not. So that's an important thing to know with limits. It doesn't matter if the function is defined at a point. We're only interested in the behavior as the function approaches that specific point. So let's do another example here. Let's say I give you the following function. Let's say, well, I'll erase this here to avoid any confusion. So I'm going to give you a piecewise function here. And this will go over another important concept of limits. So let me say f of x is equal to x squared if x is greater than 3. I'll make it greater or equal to 3. And then 5x if x is less than 3. Alright, so we got this piecewise function here. And now, first thing I'll do, just to help visualize what's going on, is I'll draw a sketch of what this graph looks like, of what f of x looks like. So we know that at x equals 3, let's say it's around here, we're going to be following the part of this function, which is x squared, which we know will look like this as it's coming out. This is going to be this function here, and it's going to be at 3, 9. That's that coordinate there. But for any value less than 3, we're going to be following 5x. And we'll see that at x equals 3 here, we'll be starting at 15. It's going to be following this line. This is what the function is going to look like at, when x is less than 3. It's going to be at 3, 15. Not actually defined there, but that's what the open circle is. That's that coordinate there, 3, 15. And let's say I ask you to find the following. Find the limit as x approaches 3 of f of x. Now we have a problem here, because if we look at this, this function doesn't seem to be approaching a specific value, does it? If we approach it from the right, we're going to see that it gets closer and closer to 9. It'll converge to 9. But if we approach it from the left, we'll see it's getting closer and closer to 15. It's going to converge to 15. So this can't be right, you know. We'll look at ourselves and we'll say, well, we don't really see a limit here. This doesn't converge to any value. And this is true. We say that this limit does not exist. This function does not converge to a specific value. And this is because there's a very important property to know about limits. In order for a limit as x approaches a of f of x to exist, the following must exist. I'll star this here because this is very important to take note of. The limit as x approaches a from the left of f of x, this little minus sign means from the left, must equal the limit as x approaches a from the right of f of x. That's what this little plus means. It means from the right. And if this is not true, then the limit as x approaches a, just in general, does not exist. These limits must exist and must be equal. So therefore, we can see that in this piecewise function, this does not actually exist. And you know, there will be times where it might actually exist. Like for example, let's say, oops, no, I zoomed in here. Let's say I gave you the piecewise function. Let's say I gave you f of x is equal to x squared if x is greater than 3, but it's going to be equal to 5 if x equals 3, and it'll be 3x if x is less than 3, right? So again, we have a similar looking graph here. We're going to have the x squared at 3. When x is greater than 3. But when x is actually equal to 3, it's going to be at 5. We're going to be having this value 3, 5 here. And then, of course, it's going to be equal to, it'll look like this for any value less than 3. So we're going to have this piecewise function. Now, if we find the limit as x approaches 3 from the left of f of x, we'll see that we'll be following this part of the piecewise function when x is less than 3, because it's from the left, so it's going to be less than 3. We'll see it gets closer to 9, because we're following 3x here, and the limit as x approaches 3 of 3x is 9. But let's say we find the limit as x approaches 3 from the right of f of x. In this case, we're following this part of the piecewise function, the part where x is greater than 3, because we're coming from the right. We'll see that it's also going to approach 9. So therefore, we'll see that also, just in general, the limit as x approaches 3 of f of x will also be 9. Because this condition up here, that the limit from the left and the limit from the right are the same and equal, that's the only condition that must be met for this limit to exist, right? So since this is true, this is also the limit at this point. The limit as x approaches 3 of this piecewise function here is 9, even though at x equals 3, it's not 9, it's 5. That's okay, because once again, with limits, it doesn't matter what value the function actually is at a specific point. It's only the behavior as the function as x approaches that point. So that's the key takeaway from working with piecewise functions and this little important thing about limits here.